Well, I have to set up. No, I have to set up. You're for now, let me be. I'm there to start it on. Well, I was like, trying to have this like open, like open, there's a way to practice. I was like, cool.
Looking cool, eh?
Yeah.
No?
I mean, yeah, I think it's cool how it makes that shape.
Yeah, but you know why it makes that shape. Come on. Yeah, since we had heard last time's discussion, I thought I'd put this up as well. Let me restart it here. I don't know how close it is to ending, but yeah. I mean, of course, you're looking at the surface of the sun here, and I believe this is taken by the Solar Dynamics Observatory. So one of the satellites that we have, one of the current missions on NASA, is a satellite that just continually takes images of the sun. So these are individual images, not a video file, but it's individual images, and then they splice them together and sped it up to kind of see the motion. So I don't know, I'd have to go and look, but this is probably, I don't know, like a month's worth of video or something, a month's worth of images, something like that. And what you're looking at, this is called a solar prominence. And what you see is the hot plasma from the surface of the sun that, for whatever reason, gets ejected into the atmosphere, okay, just above the surface. And because it's a plasma, oh, you guys, what's the formal definition of plasma?
Really hot.
Huh?
Really hot.
Really hot? Well, yes, that's how you form a plasma, but that's not, I mean, you could say that, well, I could say that my wife is a plasma then. I mean, if that's your definition, then my wife is a plasma. I'm gonna have to try that on her later. Okay, it can't go over any worse than, well, compared to your thighs aren't that big, right? Like that, can't go any worse than that, right? Okay, no, I mean, like, how do we define what a plasma is? Okay, so I could lie about it, you guys won't correct me. Okay, good to know. Okay, I think, so of course, you know, you go from solid, you add some energy, you jiggle the particles and they break apart and you get a liquid. You add more energy and eventually is it the van der Waals forces that keep a liquid confined? Is that right? Or is it the ionic bonding? Or is it covalent? It's not covalent bonding, but okay, so I can lie about it as well. Okay. Right, I mean, like, there's something about the bonding that makes alcohol vaporize at a lower temperature than water, for example. So you have the polar molecule, and that keeps water from vaporizing as quickly than alcohol. But I can't remember if it's van der Waals or if it's polar bonding. I don't know. Okay, you chemists, you'll have to take care of that for me.
Hydrogen bonding.
Okay, hydrogen bonding. Okay, so then you vaporize it, you get into a gaseous phase. Yeah, in my understanding, again, you'll have to correct me if I'm wrong, a plasma is formed by you keep adding energy to the point where you strip the electrons from the material. So my understanding is that a plasma is when you ionize, you add so much energy that you end up ionizing the gas. And so what you have are charged particles. You have a gas of charged particles, right? Ions. And I believe that that's what characterizes the plasma phase. You have a gas of charged particles. So the sun is essentially a huge ball of plasma because it's so hot that basically electrons are not allowed to bind to the hydrogen primarily. So they're all just an ionized soup of gas. And so what happens is that you get some of this ionized gas that gets ejected into the upper atmosphere. And you get this lovely loop structure. Now, yes, gravity is acting on it. There's gravitational force that wants to pull those ions back to the surface. But that's not what you're seeing here. This is not parabolic. This isn't a parabolic arc. Right? You would expect if it were just gravitational forces, you'd expect a parabola. Right? You shouldn't get something like, you notice that it goes outwards, and then it actually pinches back in. You shouldn't get that inward motion. It should just be, right? Parabola doesn't do that. So there's something else going on here. And you have an idea. Now, you're not going to sit down and give me the equations for it, but conceptually, you should be able to qualitatively explain to me what's going on here. You have a charged gas, ions, that are moving. What are you seeing in this loop structure? Yeah. So I'm not going to think about the magnetic field due to the moving ions in the atmosphere. But you are correct that there's a huge ball of moving charges down here. And that huge ball of moving charges down here generates a magnetic field. And so when you have, I'm thinking of this as your system now, just these charges here. When you have, okay, I guess I'm not going to have a pointer today. Sorry. Must have clicked. Oh, that's right. I'm not in the PowerPoint. Excuse me. So that's why it didn't work. When you have your system, I'll consider this gas to be the system and this gas down here to be the surroundings. Yeah. I don't really care about you, Microsoft. Go away. No, don't tell me more. You have a magnetic field due to the sun. When these charged particles get ejected into the atmosphere, they get trapped by the magnetic field of the sun. So what happens is they end up spiraling around the magnetic field line of the sun, which then reconnects back to the sun. They get ejected out, they get trapped, and they spiral back in. So what you're seeing really is during this process, you're seeing it twofold. You're seeing two things. First of all, you're seeing a region of magnetic field form. That's why there's no loopy structure, and you see it starts to form. What's happening is something happened inside the sun that starts generating a small magnetic field right at that location. Then the particles that are trying to fly off the surface get trapped, and that's where you get that loopy structure. And this happens all the time. You get these small magnetic I don't want to call them an anomaly. I don't want to call it an anomaly because it happens all the time. Okay? These little structures form on the surface. And again, I say little, but there's the Earth to scale. Right? These are 3 or 4 diameters of Earth in size. Anyway, so yeah, you're looking at a huge case of magnetic confinement. The magnetic field of the sun traps some of these charged plasma, and you get that structure. Okay, that's just another example. Questions on that? Again, qualitatively, you can tell me. Now, I'm not going to ask you to give me the equations, but you could qualitatively come up with something. Incidentally, surface temperature of the sun is about 6,000 Kelvin. Okay, so if you convert that into the motion, the microscopic motion of the plasma, that's wicked fast. Right? That's the technical term, wicked fast. Okay. Challenge number 2. So there's challenge number 1. We should do like challenge number. We should have a challenge day. Challenge number 2. I think I can spotlight like this. Spotlight. Okay, that takes over. Yeah, challenge number 2. Move this over here so that. Oh wait. Okay. No, this can't be done. Okay, I'll do it like this. Challenge number 2 is this. I promised I'd bring this in, and I'm sorry, it's so dusty. I thought, oh yeah, I promised that I'd bring this in at some point. And the challenge was, okay, well, can you tell me what this does? And a couple of you looked at it before class, that kind of thing. Let me put it over here. I should have taken a picture as well, but you see you have a little thing and a little mirror, and yeah, what does this thing actually do? In fact, you have this little, Oh, I got to be careful. You got this little seesaw thing that comes off, which is always nice. Yeah, yeah. No, I got to put it back on to make sure I get it right. Oh, I forgot that there's this little clamping thing too. So there's this, okay, yeah. So what does this thing do? You can describe, I mean, given a little bit of hints, you could describe what this does. And I think this is kind of historically the apparatus that you use to measure the force of the magnetic field. Say, how do you do that? Let me walk you through. Can you see that okay, Delaney? Or I'm not sure if I've got it in the right spot. Okay, can't tell. So hopefully that's in the right spot. Yeah, what does this do? First of all, what's the mirror? Okay, now what's the mirror? The mirror is not important to the entire operation in terms of functioning. The mirror makes the measurement easier. And anytime you see a mirror on an experimental piece of apparatus, usually it tends to be the same reason. Have you used anything with mirrors? What are mirrors really good at doing? Measuring angles. You say, how do you measure an angle with a mirror? Shine a laser at it, right? If I take a laser, I bounce it off this mirror, it'll put a spot on the wall. Okay? Now, the nice thing is that because of that, a small change in angle here, which might be really hard to measure, manifests itself as a huge deflection of a spot somewhere else on the wall. And the farther away the wall is, the larger the deflection is, the easier it is to measure. A small angle here results in a large arc length out there. So the mirror is not imperative to the function of the apparatus. It is solely there to make the measurement easier. Okay, so a tiny deflection here, okay? So first of all, making sure that this thing doesn't wobble is really important, right? Which is also the purpose of these magnets in the base, to be continued. But these magnets in the base are to make sure that any extraneous vibrations, any extraneous motion dies out quickly. This is a dampener. Okay, so the mirror's not important. This little vein and the magnets down here are a dampener. That's not important. And that will also explain to you why you have these masses on a threaded rod back here. What do you think those masses on the threaded rod are used for? Not the measurement. Yeah, I like where you're going. To balance it, right? This thing, I want this, if you notice, it's on a knife edge. Okay? This little triangle here is called a knife edge. And this, you adjust the weights here to make sure it's balanced so that you can do the measurement. Okay? To be continued. Give me just a second and we'll get there. Okay? So you adjust this to make sure it's balanced, just like your little handheld pan balances. Right, you got to make sure that the little thing is right on the red line. And you turn that screw until that little measurement thing's on the red line, and then you know it's balanced. That's the screw turn right here. Okay, now over here on the other side, you see this little metal thing. Okay, that's a pan balance where you put. You're going to put tiny masses right here to make to measure it. Okay, so right here on this little segment, you see how tiny that is, right? There are tiny little masses, and if you go up to the chemistry hallway, look at some of the display cases of the historical stuff, but I think they have a pan balance that's enclosed in a glass case. Like there's a wooden glass case that the pan balance is in. That pan balance is so sensitive that they wanted to isolate it from air currents. So you literally do the measurement, you put the stuff on, then you close the box, wait for everything to settle down so that the air currents don't affect your measurement. But in that case, you'll also see a little wooden box with tiny, tiny masses. In fact, it has like a little pair of, not pliers, but tweezers. Okay, little tweezers that you pull the masses with because they're just so tiny. And also, you don't want to put your oil on your fingers on those masses, so that affects the mass of the masses. That's how precise and fine those masses are. Sometimes the oil on your fingers can affect the mass, and so you use tweezers, that kind of thing. But that's what goes right here. Now imagine for a second, I don't have any masses on this, it's perfectly level. Okay. The last thing that we've got to figure out, I've got my laser shining on the mirror and I've marked the spot. The last thing we got to figure out is what are we actually measuring? What do we want to measure here? And that's where you notice these 4 posts. Right here and right there. There's 4 posts on this apparatus. And when you see those, what do those remind you of? I'll turn it sideways so that everybody can see. So you got a post here, you got a post there, there's one over here and one over here. And oh, notice between the post here and here, there's a metal bar. Oh, and notice between this post, you go through the knife edge. You go down this bar, you go across this bar, you go back and out through that post. What are you supposed to hook up here? Like a power supply? I'll go the other way. A power supply will work. I'll do a current supply. Something that can provide a source of known current. I can hook up a current supply here and run current from this terminal up through the knife edge, because that's a physical connection. It's metal on metal, so that's a connected circuit. Down this wire, across, back down, and out that post. Same thing, I can hook a current supply up to this front post, run it down the wire, and out through this post. So let's imagine that we do that. We have now 2 wires carrying ideally the same current. I'll hook up the same power supply to both posts. So now I have 2 wires that are carrying parallel current. I got to think about this for a second. Let's see if it goes this way. Okay, let's say for the bottom wire. Oh yeah, go ahead, Isaiah.
An example to select like which directions of the current you're running.
Both. You'll have the negative charges running one way and the positive charges running the opposite way.
Like is the movement of it, the direction the charges are running, or like an opposite?
It'll spiral. So one set of charges will spiral one direction, and then the other set of charges will spiral the opposite way.
Oh, okay. So that's like the movement that you're seeing?
Yeah. It turns out when those charges crash into each other, they heat up, and that's what's giving off the light. Yeah. Okay, so if I have this front post, let's say we run current going this way, to your left. Let's take this out of the way for a second. So say we're running current to the left. What's the direction of the magnetic field due to that current carrying wire? Let's say above the wire. What direction is the magnetic field? Yeah. Take our thumb, let's run it in the direction of current. Pretend that we grab that wire, and above the wire, the magnetic field's pointing towards me. Good so far? Grab the wire, it's going towards me. Okay. So now we have our surroundings, the bottom wire. Here's my system, the top wire. Okay. So now the top wire is running a current this way as well. I said the currents are parallel. Top wire is running a current that way, and it sees a magnetic field that's going towards me. What force will that top wire feel if the current is running that way and it feels a magnetic force going that way? It'll feel a force going down. Okay. So if I run a current parallel in both of these wires, what should happen? The top bar should shift downwards, should be attracted. How about if I run an anti-parallel? So let's say in the bottom wire, it's still going to your left, and in the top wire, it's going to the right. What direction is the force on the top wire due to the magnetic field of the bottom wire? Current in the top wire is running to, sorry, I said my left, your right. Magnetic field due to the bottom wire is pointing towards Greg, so that's the palm. The force is given by the thumb. So if I run the current anti-parallel, one way in the bottom wire and the opposite way in the top wire, I should see a repulsion. How is that going to help me measure the magnitude of the magnetic field? These two wires repel. Oops. This is where we'll throw it all together. I can measure the distance between the two wires if I need to. Yeah. What's this little thing here for? I'm sorry? Now you got it. Right? Imagine for a second, I balance this thing. I mark the spot on the wall. I run a known current through the bottom wire and anti-parallel through the top wire so that they repel. The next thing I do is I take my tweezers and I start adding masses to this little pan. And as I add masses, closer and closer together again. And when do I stop adding masses? When it reaches, right, I've got the spot on the wall, I mark it. I turn on this current, it deflects. I add masses until I've got back to the spot where it originally was. What's the net force on my system now? If it's back at its original position, it's balanced, it's not moving. 0. Now I have a way of measuring what the magnitude of the magnetic force is. It has to be equal to the gravitational forces of the mass that I've added to the pan. I change the current value. I get a different deflection. I measure the masses. Right, I change the current. I get a different deflection. I do it again. I did. So you change it. You change the magnitude of the current, and eventually you can get an idea about how the strength of the magnetic field is related to the current through the wire. Yay, nay? This is you remember the electroscope from like week 1? This is kind of the magnetic version of the electroscope. How do you get an idea about forces and currents? You can use this kind of apparatus. Just like you can use the electroscope to get an idea about forces and charge. The electroscope, same charge is on the 2 vanes. You can measure the separation distance and get an idea about the magnitude of the force. Oh, incidentally, you know the mass of the little vanes. Same idea here. Same current running through the 2 wires. You can measure the force by measuring the masses that you put on, and then you can get the relationship that way. So that's at least, that will give you an idea, okay, well, the force is proportional to the current, linear. Oops, okay. You know, there's some other stuff about the magnetic field and yada, yada, yada. Anyway, when you see a mirror, usually that means you're doing lasers to make a measurement. To make it easier. It's not that it's necessary, it's that it just makes the measurement a whole lot easier to do. Anyway, yeah. I'm sure you've already, I don't know, put that here. What is this for? See, I haven't figured out what this little thing is for. I think that's just to hold the bar when it's not being used. So incidentally, yeah, I don't know how good this is, but of course, this is really dependent on making sure that knife edge is clean, right, and that it's sharp. So if you ever see like a knife edge, you want to, I mean, aside, it's not going to cut you, it's not sharp enough to cut you, but like the reason it's there is to have a really nice balance. Okay? So anytime you have something that uses a knife edge, just be careful, you want to protect that edge. I have not been doing very well at protecting that edge, but I don't know when the last time this apparatus was used. I mean, I guess technically we could use it in lab. Yes. I just don't know how much current you have to run. That's the one thing that scares me. Like, what kind of current supply do you actually need to run this thing? Yeah. I don't trust stuff that's, no, I trust it. I don't trust me to be aware of when I can hurt myself with that. That's what it is. Like, I'm sure the people that designed that had a full intention, like, okay, this is a wonderful idea. I just don't trust myself not to hurt myself with it. Right? Did I already mention that wonderful toy in the 1950s that came with like power grade uranium? Oh man, wish I could find one of those. Lawn darts, you remember lawn darts? Oh, it's this wonderful game where you put a circle on the ground and then you stand like 15 or 20 feet away and you literally throw this 1-foot dart into the air and see if you can hit the circle. So it's kind of like horseshoes, but with darts. Yeah. At some point somebody said, gee, should we be throwing 1-foot darts into the air to come down on the ground with little kids running around? That seems like a bad idea. That's like, hey kids, go and play on that Olympic javelin field. Just have fun. Seems like a bad idea. Okay. So let's take spotlight mode off. There we go. Questions? Presenter mode. That's just trying to give you some sort of sense of what's going on there. Okay, well, let's move onwards and upwards. The last thing I was thinking about, and then we're not getting rid of the magnetic fields. We're not going away from that. We've got to deal with Faraday's law, which goes into a discussion about induction. But this is the last thing I thought we should talk about is magnetism in materials. Okay. We started out this thing, I said, hey, materials that tend to be more susceptible to magnetic field, the materials that respond well to magnetic fields tend to be the materials that have a lot of unpaired spins. And now hopefully you've got an idea about that unpaired spins of the electron cloud mean that you have a large circulating current. A large circulating current can be modeled as a small bar magnet, and you can go on our merry way. The question that we have not yet answered is why is it that a hunk of iron isn't just automatically magnetic? Right? We've made an argument so far that iron should be magnetic due to the unpaired electrons, yada, yada, yada. So why is it that when I take a hunk of iron out of the ground, it's not automatically magnetic? What's going on there? How do we actually create a magnet out of iron? And the whole answer comes in when you start thinking about torques on current-carrying loops. We think about torques on current-carrying loops, then we can get an idea about how do we form magnets out of iron. Why isn't iron just automatically a magnet? Why do I have to do some sort of extra processing to it? And once we get an idea about that processing, then you also have an idea about how you destroy a magnet. In fact, you're probably already aware of how to destroy a magnet. Okay, well, we'll do it then. So let's start with this. We got to talk about torques. I've got an external magnetic field for you. I've just drawn that in. Let's go ahead, for sake of conversation, let's assume that it's constant. Okay. So let's not make our lives difficult. It is a constant magnetic field that's going in the negative y direction. For some reason, I decided to do my axes like this. Oh yes, I know why. Be careful if you ever find yourself in a math class, okay, that's dealing with vectors. The reason I say that is because in physics, we tend to put y as being up. We tend to put x to the right, y being up, and by the right-hand rule, that requires the z-axis to come out at you. Mathematicians prefer to put z as being up. They're kooky, I know. Just be aware of that. This coordinate system with x coming out at you, y to the right, and z being up, that tends to be the coordinate system that mathematicians will use. They're weird. Okay, let's all agree they're weird. And yeah, I say this in the fondest sense. I was also a math major. I ran into some weird people. They're all weird. Except me, of course. I've never met a weird mathematician. Or I've never met a non-weird mathematician. I keep trying. I find the only one that seems to be normal is me. Same thing with physicists. All these physicists seem crazy. Why can't anybody be the normal like me? Okay, so I've got the magnetic field going to the negative y direction. I've put a side view in here, and let me draw the loop. Okay. So, and I apologize, that's probably a poor color choice now. I should recolor the magnetic field, but we'll live with it for today. So I've got a current carrying loop. I put it on an insulating pivot. I just wanted to indicate about what location is this thing going to rotate. And I've gone and I've said, okay, let's run current in our system, our loop, and I'll run it clockwise. So I want the loop to be the system, and then I have this external magnetic field. And I want to know what will happen, what will this loop do? If this loop is free to pivot, to rotate, what will this loop do? Now this side view is a bit hard to kind of analyze. So I've got another view on the right-hand side of the screen here. I imagine going from this side view, and we're going to rotate over top, so we're looking down on the pivot. So we jump in our little spaceship, and we're going to get up here and then look down on the loop. Okay. Oh yes, and I've given you a distance of L and 2R, the length of the loop and the width of the loop. So here is the same image. It's just that instead of X coming out at you, we have gone up so that we're looking down on it, like the overhead view of the loop. So my magnetic field is still running off to the left. And you notice now I've changed my axes to be consistent with this top view. The Z-axis is pointing at you, the X-axis is pointing towards the bottom, and yada, yada, yada. It's always helpful to kind of redraw it. So here's my loop now, as seen from above. On the left-hand side, current is coming up, going in the positive Z-axis. So the left-hand side, that current is running at us. On the right-hand side, negative Z-axis. So from that top view, it's running down the wire, going away from us. This is, again, just to kind of get ourselves oriented. The side view I find more informative to see what's going on. The top view is easier to analyze with our physics. So that's why I've put both of them in here. Okay so far? Question. No. Let's start off with this. I have current running towards me. If I want to think about this part of the wire right now, just think about that. What's the direction of the force due to the magnetic field on this segment of the wire? The segment of the wire that's carrying the current towards us. What direction is the force of the magnetic field on that segment of the current carrying wire? Or the current carrying loop, I should say. Yeah, I gotta think about it too. Let's sit here. So this way, or this way. Okay. I should see you guys being doing some sort of Tai Chi maneuver right now. You know, like, I don't know if that's fair to say. I guess I probably shouldn't say that, sorry. That's an old holdover, right? My professor said, if you're not doing Tai Chi during the exam, you're not gonna get 100. You should see yourself kind of doing this, right? Yeah, remember, the direction of the force is given by running your fingers in the direction of the current. Shoot, I forget how I represented that now. They just call it L. They call it delta L, is that how I represented it? Stuff is blurring together. All right, run your fingers in the direction of the current, I. Point your palm in the direction of the magnetic field, and your thumb will give you the direction of the force. So I run my fingers in the direction of I, point my palm in the direction of the magnetic field, my thumb gives me the direction of the force. So for this part of my current carrying loop, the force should be down. Oops, muscle memory. There we go. Force should be going down in the positive X direction. Yes?
So I get I on the side. How do you go from like transition where your fingers point from I to the side view to the top view? Like I'm just having trouble visualizing.
We should be able to do the same thing on the side view.
So I can still run my fingers the same way it's run.
Yeah. So if you're thinking the side view, I is going this way. Your palm is going to the left. Your force is coming out of the page. Now on the side view, what direction is out of the page? The X direction. Yeah, so the X direction is coming out of the page. Okay. Notice if we do the top view, the current is running this way. The magnetic field is running still to the left. My thumb points down. And from this top view, down is which direction? X. Yeah. So it shouldn't matter if you look at the side view or the top view, you'll still get that the force is in the X direction. Yay, nay?
I guess.
Yeah. You say I guess, and you didn't convince me. Black, blue. Do we have a red? Okay, green is the best we can do. Side view. X coming at you. Z is up. And Y is to our right. Now go ahead, stand up. Huh?
I don't want to stand up.
No, you gotta stand up. Yeah, no, come over here. Sorry, maybe I should have put it there, that you didn't have to stand up. And just look over it. Right? So remember, this is X, this is Y, this is Z. Okay? Now just look over it. Now what does it look like? Which way is X pointing? That way, Y is pointing this way, and Z is coming out at you. Okay? So, I'll take that. So I went from, okay, I should have done this. Yeah, you can go ahead and sit down. I should have done it like this, maybe. Right, I have it like this, where X is pointing out at you, Z is coming out, Y is coming this way. All you've done is you've shifted so that now you see the overhead view. Which is the axis that I used on the overhead view. That's like, you looked at it at the side, you decide to stand up and look over it, so it'll look like this to you now. Unfortunately, it's hard for me to draw it and have you stand up and look at it at a different position. So I just redraw it for you. Yay, nay?
Yeah.
Okay. It takes a little bit, yeah, like that visualization process is sometimes takes a little bit, yeah. Okay, which one of these was actually the good marker? Okay, I think blue goes here, I think green goes there, and blue stays with me, or black stays with me. Okay. Other questions? Yeah.
So when you say force associated with the magnetic field, is the force acting on like the wire itself, or is it acting on everything around?
It is acting on, I guess technically it's acting on the charges which are moving through the wire. I would say acting on the wire. Yeah, if you pressed me, I would say yes, it's acting on the wire. Does that answer your question? Or?
Well, it's just like, is the force, like, let's just say for the thing that you're talking would the force, caused by each one of the wires be acting on the other wire or the wire itself?
Force, I am considering the current carrying loop, the entire loop as my system. And so I will not worry, I would like to know the net force acting on the system. So to find the net force, I'm looking at the force that acts on each individual piece of my system, and then I'll add it together at the end. I also am not worried about, maybe this is also, correct me if I'm still missing the mark, you got to let me know. The other thing is, I am not worried about the magnetic field generated by the current carrying loop. That is considered to be part of the system. So the magnetic field that is being generated by the current carrying loop does not affect the system. Because if it did, that means that I have a way of exerting a force on myself, which is a no-no. System is not allowed to exert a force on itself. So yes, this current carrying loop generates a magnetic field. I do not worry about that because that is, if you will, part of the system. So I can ignore that piece. Does that get at it? Okay, okay, finally, it's like I don't feel like I'm quite getting, okay, yeah. Other questions? Yes?
For the right-hand rule we just applied, is that only for the external magnetic field? Because I know we talked about the one where you point your thumb in the direction of the current. Is that for the current or the magnetic field generated by the current?
Correct, yes. So you have one that says you have a current, what's the magnetic field generated by that current? That's, I run the thumb in the direction of the current, my fingers give me the direction of the magnetic field generated by that current. Okay. Now, the second one, where we also use the right-hand rule, is yes, the force of an external magnetic field on a current. Yes. So when I did this, I should say the current of my system and the external magnetic field. Yes, to be more specific. Good, good, good. Of course, this also could end up being, instead of this, it could also be the charge of your system times the speed, and then you still have the external magnetic field over here. So if it's an individual charge like your mass spec, as versus a current carrying wire, like. Yeah, what else? What else you got? How about the other wire? We took care of the one where the force is coming, or the force acting on this segment of the wire, of the loop. How about the force acting on this segment of the loop, where the current is going into the board? What direction is the force acting on that segment? Yeah. Good. That one is going. That one's going up. And the overhead view, I guess. Let me see here. On the side view, okay. Magnetic field. Okay. Sorry. Just to be consistent, I'll put it on the side view as well. So the force is coming out at you, and for this one, the force should be going in. Just to have it on both. Good. So we've got directions now. We know that the force on the wire that's carrying current out is going in the positive X, and the wire that's going in is going in the negative X. Oh, I should ask you another question. How do those two forces compare in magnitude? What's your gut tell you? The magnitude of this force, how does it compare to the magnitude of that one? It should be equal, right? The force is going to be proportional to the current, they carry the same current. The force is going to be proportional to the length of the wire. Well, both of those wire segments are the same length. So the force acting on this wire segment will be the same in magnitude as the force acting on that wire segment. Which means the net force zero, right? You add one to the other, you get zero. In other words, this loop will not undergo any translational acceleration. Right? The net force is zero, therefore the translational acceleration is zero. And you go, wait a minute, why is Greg being very careful to say translational? Question. What about the rotational acceleration? Will it accelerate? Survey says yes. Not translationally, but rotationally. This will not translate, but it will rotate. And what do we call a force that causes a rotation? A torque, which is why I titled the slide, torque on a current carrying loop. Right? Right? So we're not talking about translational accelerations, but rather a rotational acceleration. The presence of a current carrying loop in an external magnetic field causes the current carrying loop to rotate, to undergo a rotational acceleration. Which way is the torque? Just out of curiosity. I agree, the object will rotate in the counterclockwise direction. And we say that the torque, therefore, is coming out at you. I think Leo did the right-hand rule with torque, curl it in the direction of the rotation. The torque is the direction of your thumb. Yeah, so this thing will undergo, let's see, a torque. The torque, we'll put net torque, is parallel to z direction. Did you use z hat? Have you seen? I can't remember if I've used z. No. Okay. Torque. The net torque is in the z direction. I'll call it z direction. You want to find the magnitude of the net torque? You did that in the homework? Okay. Probably. You want me to run through it, or are you guys okay with it? Matters not to me, I can do it if you want. Quick definition of torque. I'm sorry? We again use our right hand rule. I'm not sure how Leo, it sounds like how Leo taught it was for torque. You curl fingers in direction of rotation. I don't know if rotation is the right word. I should say angular acceleration. And then your thumb gives torque direction of torque, something like that. So you curl it, you know that it's going to, if it's stationary, it will begin to spin counterclockwise. Curl your fingers in that direction, the torque will be out of the board. Sorry, just a second, let me make sure that I have a couple extra blank slides here, otherwise I don't know if I actually planned on. It's okay if I throw up a blank slide here. Exit out. Exit out, blank slide. There we are. From current slide. Okay, let's just do it real fast. Okay, yeah, we'll do it. Torque is, one way to do it is the perpendicular distance times the force. And if I want to find the net torque, torques obey the principle of superposition. If I want to find the total torque, the net torque, I can add up the individual contributions. So for this situation, the current carrying loop, the net torque is given by the torque of the wire carrying the current coming out, plus the torque of the wire that carries the current going in. All right, I'm just using those subscripts to remind myself, the wire coming out, the wire going in. Now in the definition of torque, when you're, I don't know, I should double check. Do you remember what that R represents? When you're thinking about torques?
Distance from the pivot to where the force is at.
Good. The distance from the pivot to where the force is being applied. Now, if we go back and look at my figure, which is several slides away now, I had top of the loop was a distance of 2r, and the pivot point was right in between, right in the middle. And the force acting on this side is going down, the force acting on this side was going up. So yes, this R is the distance from the pivot point to the point of application of the force. So in the dimensions I gave, this R perpendicular is that distance. For the left-hand side, and of course it's that distance for the right-hand side. If I call the whole thing a distance of 2r, then these half distances, not by accident, are R. When's Talk Like a Pirate Day anyway? I'm not making this up. Well, somebody made this up. There's a Talk Like a Pirate Day. I don't know. You know, just like National Donut Day. Like, okay. Okay. Good. So each of these is R. And notice that R is already perpendicular to the force. Right? The force we said was going down, that's perpendicular to that distance. This force is going up, that's perpendicular. And so if we want the net torque, we can just say it's R times the force of the magnetic field. I'll say acting on the inwards wire, out wire, times R times the force of the magnetic field acting on the current carrying wire going into the board. So all we need to do now is substitute in our expression for the magnetic force acting on a current carrying wire. I'll go ahead and write that down. It's the current in the wire times the length of the wire, which we had as L, times the strength of the magnetic field, B. You guys have to let me know if I'm going too fast. Are you following along? Just making net torque phase superposition.
So can we just assume that, so are we assuming the torque happens right? How do we know where on that, all 2R the torque is happening?
Oh, yeah.
Split it in half and not a third and 2/3.
Yeah, so one thing is I set up the problem to make sure that the pivot was right in the center. And the second thing is that, remember, the force is actually occurring on that piece, that wire that's going, either out of the board or into the board. It's not occurring along the length of the arm.
And if it was occurring on the wrong, that we have to add like the same.
Yeah, let's see here. If it were acting along the length of the arm, that would mean that, I'd have to give you some more information. Yeah, I'd have to tell you how the arm is angled to the magnetic field. Yeah, it's not by accident I set this loop to be parallel to the magnetic field. Yeah. Does that help out though? Is that answering your question?
Yeah.
Okay. I believe we are now officially done. Let's go ahead and I'll go ahead and just sub that in to that expression. And we notice because the I's are the same, the L's are the same, the B's are the same. We've already taken care of our direction with the right-hand rule. That's where this addition came in. Okay. So the only thing left is we get R times L, ILB. And of course, we'll get the second expression. So I'll just put a 2 out front. There we go. The net torque acting on our current carrying loop is given by 2RLIB. Now the last piece of magic, now this is a heuristic argument. This is not a formal proof. This is a heuristic argument. Notice the quantity 2R times L. And I'll put IB here. In terms of our original problem, 2R times L. What does that represent in our original problem? That's the area of the current carrying loop. Now, this is not again, a formal proof, but this is just a heuristic argument, is that you could actually apply this to any shape as long as you have the area. So the torque acting on a current carrying loop is given by the area of the loop times the current running through that loop times the magnetic field. So if you have a circular loop carrying a current in a magnetic field, you can figure that out, et cetera, et cetera.
We'll be getting in square meters, right?
I'm sorry?
You'd be getting in square meters, right?
If you want to use a magnetic field strength in Tesla, then your area needs to be in meters squared. Yes. Yes. If you want to use the internet SI units, yes. Which, I mean, we've already seen what happens when Greg tries to program a problem with not SI units. And he just spends all evening manually grading stuff and rerunning grades. I'm sorry, you're gonna suffer that one, but next year, you've paid a price that next year's students won't ever have to pay. So you can go around to your students next year, and when they're blabbing about how horrible 185 is, you can say, back in my day, you asked us for non-SI units. Okay. You can tell them how horrible your experience was. And also how you had to walk to class in the snow, which will be true. Not the whole time. And maybe you could even argue you had to walk uphill. Let me tell you, in my day, it was snowing, we made us use non-SI units, and we had to walk in the snow. It was also muddy, because they didn't have sidewalks in our day. All right? All right. You now have a good idea about what you have to do in order to get iron to be magnetized. If you take a current carrying loop and you expose it to a magnetic field, okay? Oh, well, here's an example. Yeah. In fact, I don't know if I have the audio here. Sorry, this is an overhead view. And remember, we use compasses to test for the presence of a magnetic field. Oh.
We have some iron filings here. And we notice that when we bring the iron filings close to the compass, nothing fancy happens. So that's step one. Now, the next thing that we're going to do, we're going to take our iron filings, and this might be a bit hard to see. I'm going to take this magnet, and I'm just going to start on one end of the iron filings, and I'm going to drag that magnet to the other side.
You can kind of see right on the edge.
And you can see at the edge at least, right on the edges here, you can probably see those little iron filings moving just a little bit. And let me do that again, and maybe one more time.
Don't let go of the magnet, it'll shatter the tube, by the way.
Physically moving. Now let's go ahead and let that compass settle down for a second. And again, I'm going to very carefully, I don't want to jostle the iron filings, but I'm going to very carefully bring it in. And now you see, indeed, I have some sort of magnetic field, right? That compass is now responding to the influence of those iron filings. Let's go ahead, let's see if we can do this as well. I'm going to very carefully bring the other side of that test tube near the compass. So the side that has the black tape on it. You see now, okay, it's pushing the needle away. Very cool. Now the last thing, what did I really change here?
Oh yeah, I should stop.
Themselves, but rather,
Yeah, what did I change? I mean, same tube. Terrible animation. You're not supposed to agree with me, Ben. What are you talking about? You do better. Good gravy. Man, you can talk about me behind my back, but man, that was just brutal. Hey, what did I change?
The alignment of the iron filings.
The alignment. Remember, what happens when I take a current carrying loop, in other words, an iron atom, I expose it to a magnetic field, that my iron atom will experience a torque. In fact, furthermore, it will turn to align itself with the magnetic field. Now, you can see it with the iron filings. You can physically, as you drag that magnet across, you can see the iron filings shift a little bit. What you're doing is using the magnet to exert the torque that caused all of those iron filings to go the same way. Notice I was very careful. I drag it up from one end to the other, and I do it again. Like, I don't drag it back and forth. You go start on one side, drag it all the way to the other, and just repeat that. So yeah, the only thing I've changed is how the iron atoms are arranged, which gives you an idea about what I need to do to get rid of the magnetic field. What do I have to do to get rid of the magnetic field in this test tube? Shake it, right? Let's just Taylor Swift this sucker, right? I should have put that song in there. That would have been great. That Ben would have approved. You've been like, yeah, Taylor Swift.
Test tube of iron filings, I actually changed the orientation of those filings. I've managed to orient them in such a way that now they have some net magnetic field being produced. So how do I destroy this? How can I get rid of this magnetic field in my iron? How can I get rid of this magnetic field in my iron filings? Well, that's simple. Let's just remove that alignment. If the magnet...
Okay, great. You talk too much. Blah, blah, blah. Shake the sucker.
Iron filings, all I have to do is disorganize.
There we go.
Those iron filings. I'll just give it a shake, and now we see that influence, that magnetic field has gone in.
Okay, good.
So
There we go.
that's just a...
Greg's impatient. Yeah. So there we go. No, that's with iron filings that you can physically see moving. But the same thing happens if you can't see them moving. Oh, excuse me. Let's go there here. Yeah, so you got your iron, and in a solid material, you have the orientation of the current carrying loops are all randomized, right? You get a hunk of iron out of the ground, those atoms are just all in whichever way. What you can do though is you can expose it to a magnetic field. And what actually makes it even better is that rather than using solid iron, one way that you do this is you heat it up a bit. In fact, you heat it up high enough that it's not solid, but it's liquid, right? You want to heat it up to a point that allows these atoms to very easily rotate. So take a hunk of iron, heat it up until it's liquefied. Next step, expose a magnetic field. And that will allow the iron filings to orient themselves with the magnetic field. All those iron filings, or those atoms of iron, will respond to that torque and orient themselves so that they're all aligned.
Wait, can you go back to the other side real quick?
Okay, they're just random. Yeah, I just meant for this to represent randomization. But then when I liquefy it and allow them to easily move, they will all torque so that they're all aligned. Next step, cool down the iron. Don't leave it liquefied. If you allow it to cool down, it'll eventually solidify. It will lock the atoms into place. It will not allow, they won't rotate anymore. And then last step, just remove the magnetic field. Because you have now forced these atoms into an alignment, and then you remove the magnetic field, all of the current carrying loops are now generating their own magnetic field, and those all are aligned in the same direction. You've taken your piece of iron and turned it into a magnet. So one way you can destroy a magnet: blunt force trauma. Right, and I've got another video of that. Right? The other way you can destroy a magnet: heat it up. If you heat up a magnet to high enough temperature, then you will cause the atoms that are aligned to start jostling around so that they're not. And then if you can destroy that alignment of the atoms in the material, you can destroy the magnetic field. It'll turn back into a regular piece of metal. Now I won't go in, there's like, paramagnetic and diamagnetic. I mean, all those mean is a paramagnetic, when you do that rotation, it aligns with the field. Diamagnetic means it goes the opposite way. So, I mean, that's just kind of a small thing that I don't really care about. I know it's important, like oxygen's diamagnetic. If you expose it to a magnetic field, it will actually rotate in the opposite direction. Okay, yeah, blah, 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 blah. Okay. Yeah, I already did that. What did I? Okay, I don't care. So here's the other one. Same idea, it's just now instead of doing it with iron filings where you can visually see it happening, I'm doing it with the solid wire. The same idea is going on, it's just that you can't actually see everything rotating. But nonetheless, let's see here. So I'll do the exact same thing. Is there a way to speed this up? No, you're screwed. You're listening to 3 minutes of great sultry voice through a microphone. Okay, double check. Always good. I did this once, I couldn't figure out what's going on. The paper clip was already magnetized.
Orient the iron in this paper clip so that it is all pointing in roughly the same direction. So I'm just going to take that magnet, I'm going to run it down the paper clip. Now, of course, we can't see the iron atoms actually aligning, actually physically rotating in response to this magnetic field of this neodymium magnet. But I assure you that's indeed going on. So I'll pull my magnet away. Let's make sure it will rotate the compass. So we have some idea about the reference. And now what I'll do is I'll just bring in this paper clip. Now we see that's the the indication that somehow I've aligned some of these iron atoms inside the paperclip. And you see now it actually has some sort of interaction with that compass needle. Let's rotate it the other way. Let's see what happens if I rotate it the other way. Ah, right now instead of attracting the compass needle, it's pushing it away. Once the other side, the back end of the needle. Okay, very good.
Yeah, let's destroy this sucker.
Get rid of this magnetization. When we were dealing with the iron filings, all we had to do was shake the bottle, and that got rid of it. How about for a physical object? How do I microscopically arrange, randomize the atoms in here? Well, one way to do it, here we go. Let's just.
First time I've done this video, you can clearly tell.
Excuse me, paperclip. I'm going to randomize the atoms, blunt force trauma. Again.
Desk is,
Again.
don't do this on a desk. Incidentally, I've got some holes in my desk that weren't there when I first inherited it.
So now let's see. Does it interact anymore? Ah.
I feel like I should be a magician.
Manage to demagnetize the paper.
Okay.
Again, although.
You get the idea. So one way to do this is you just jostle, you physically hit the magnet enough times to physically rearrange the atoms. Wait, I have a comment, don't I? Maybe we should start a YouTube channel. Physics with Homie G. Oh, did you see the new one from Mark Rober? Glitter Bomb 3.0? Let's glitter bombs call centers, like scammers from call centers. Okay. Okay, so that's all I got. But yeah, I mean, now you've got a sense of microscopically what are you doing on these atoms to get them to arrange and magnetize. So that should also give you an idea about why you can't separate a north and south magnet, right? You can't get a north and south pole separated. They're both formed by the orbit of the electron around the atom. Okay, okay, hey, get out of here. Have a good weekend. I'll see you Monday.